Here is today's problem. X raised to the power of the square root of x equals 1/16. The task is to find every value of x that makes this equation true. We start by getting a feel for the two sides of this equation. On the right we have 1/16, which is 1 over 2 to the fourth. As a decimal, that target is 0.0625. It is a small positive number, sitting well below 1. On the left we have x raised to an exponent that depends on x. The base and the exponent move together, so we test values first. A natural first test is x equal to 4, since 16 is 4 squared. With x equal to 4, the square root of x is 2, so the left side becomes 4 squared, which is 16. 16 is the reciprocal of 1/16, so this misses the target. In fact, any base above 1, with a positive exponent, stays above 1. So a working x cannot be bigger than 1, and we look lower instead. And x equal to 1 gives 1 to the power 1, which is just 1. That is not 1/16 either, so we move into the fractions. For x between 0 and 1, the base is below 1 and the exponent is positive, so the output lands below 1, which at least points the right way. We try x equal to 1/4, keeping everything in powers of 2. The square root of 1/4 is 1/2, a clean value. So we are computing 1/4 raised to the power 1/2. That asks for the number whose square is 1/4. The answer is 1/2, since 1/2 squared is 1/4. 1/2 is far from 1/16, so we keep hunting. Next comes x equal to 1/16, the number from the right side. The square root of 1/16 is exactly 1/4. So the left side is 1/16 raised to the power 1/4. That is the fourth root of 1/16, and it equals 1/2. It works because 1/2 times itself 4 times gives 1/16. So two very different inputs both produce the exact same output. Both 1/4 and 1/16 landed exactly on 1/2. We go smaller still and test x equal to 1 over 100. Its square root is 1/10, so we need 100th to the 1/10. That equals 10 to the power minus 1/5, about 0.63. Making x tiny did not make the output tiny, it drifted upward instead. Each test lands around 1/2 or above, never close to 1/16. The outputs refuse to drop, but tests alone do not settle an equation. Guessing has stalled, so we switch to algebra and attack the structure. The square root sitting in the exponent is the piece that blocks us, so we give that square root its own name and substitute it away. Let capital T stand for the square root of x in this problem. A square root is never negative, so t is 0 or positive. If t were 0, then x would be 0 as well. The left side would then be 0 raised to the power 0. Depending on convention, that is either 1 or undefined. Neither option equals 1/16, so t is strictly positive. Squaring the square root of x returns x, so x equals t squared. And the exponent, the square root of x, is exactly t itself, so the equation becomes t squared, raised to the power t. A power of a power multiplies the exponents, by the standard rule. 2 times t is that product, so the left side is t to the 2t. Our equation now reads t to the power to t equals 1/16. To trust the rewrite, we can test it quickly with t equal to 2. T to the 2t is then 2 to the fourth, which is 16, and directly, x would be 4, where we already computed 16. The rewrite matches the original, so the substitution is safe. An exponent of 2t means we square the quantity t to the t, so the equation says t to the t squared equals 1/16. A number squares to 1/16 when it is 1/4 or minus 1/4. Here the base t is positive, and a positive base keeps every real power positive. So t to the t is positive, and the negative option falls away. That leaves a cleaner equation, t to the t equals 1/4. To free the t from its own exponent, we take the natural log of both sides. That move is allowed because both sides are positive numbers. On the left, the log of a power drops the exponent down in front, so the log of t to the t becomes t times the log of t. On the right, the log of 1/4 equals minus the log of 4, and the log of 4 is 2 times the log of 2. The log of 2 is about 0.693, so minus 2 log 2 is about minus 1.386. Our equation is now t times log t equals minus 2 log 2. We keep the exact form and the decimal side by side. In decimals, t times log t must reach minus 1.386. To know whether that is reachable, we study t log t as a function. Define h of t as t times the natural log of t, for positive t. From the earlier scouting, x sits below 1, so t sits below 1 too. Still, h is defined for every positive t, so we map all of it. The question becomes whether our target number is in the range of h. To map the range, we look for the lowest point of h. The derivative of h comes from the product rule, one piece at a time. The derivative of t is 1, giving 1 times the log of t. The derivative of log t is 1 over t, giving t times 1 over t. That second term is t over t, which simplifies to 1. So h prime of t is the log of t plus 1, and nothing else. For the lowest point, we set the derivative equal to 0. The log of t equals minus 1 exactly when t is 1 over e. The constant e is about to 0.718, so 1 over e is roughly 0.368. Now we check what kind of point this critical point really is. Differentiating again, the second derivative of h is 1 over t. 1 over t is positive for every positive t, so the curve bends upward. An upward bend at a flat point means the bottom of a dip, so t equal to 1 over e gives the global minimum of h. The minimum value is 1 over e times the log of 1 over e. The log of 1 over e is exactly minus 1, so the lowest value h can ever produce is minus 1 over e. In decimals, that floor sits near minus 0.368. It helps to see the rest of the curve around that dip too. Below 1 over e, the derivative is negative, so h is falling. Above 1 over e, the derivative is positive, so h is rising. As t slides towards 0, the small factor t crushes the log, so h drifts back up towards 0 from below on that side. At t equal to 1, the log is 0, so h is exactly 0 there. Beyond 1, both factors are positive, and h climbs without bound. So the whole picture is one shallow dip, floored at minus 1 over e. Now we place our target next to that floor and compare. The target is minus 2 log 2, about minus 1.386. The floor is minus 1 over e, about minus 0.368. In exact terms, 2 log 2 is much bigger than 1 over e. The target sits far below the floor, almost 4 times as deep. A function can never output a value below its own minimum, so there is no positive t with t log t equal to minus 2 log 2. Every allowed value of the square root of x was such a positive t, so no positive value of x can satisfy the original equation. The case x equal to 0 already failed with 0 to the 0. For negative x, the square root of x is not a real number. So on the real line, negative inputs never produce a left side. That covers every case there is positive, 0, and negative. Over the real numbers, this equation has no solution. The solution set is empty, and that is the complete answer. To finish, we verify the floor computation with concrete numbers. The minimum sat at t equal to 1 over e, and x equals t squared. So the lowest point of the left side is at x equal to 1 over e squared. 1 over e squared is about 0.135. The square root of that x is 1 over e, about 0.368. The log of 1 over e squared is exactly minus 2. Multiplying, the exponent times the log gives minus 2 over e. That product is about minus 0.736. Raising e to that power gives about 0.479. So the smallest value the left side ever takes is near 0.48. The target, 1/16th, is 0.0625. The gap between them is enormous, close to a factor of 8. Our fraction tests gave 1/2, and 0.63. All of those sit above the floor, exactly as the curve says they must. In x terms, the left side starts near 1 for tiny positive x. It dips to about 0.48, near x equal to 0.135. It returns to 1 at x equal to 1, then races upward past that. It passes through 16 at x equal to 4, matching our first test. Nothing on that entire curve ever touches 0.0625. So the conclusion is verified from both the algebra and the numbers. No real value of x makes x to the square root of x equal 1/16th. That is the full solution, and the answer is the empty set. Thank you so much for watching this one all the way to the end. A like and a subscribe are appreciated, and they support the channel. We will see everyone in the next video with a fresh problem to solve.